Okay, so we are ready to start the next session, and we start with Zeeshan, who will tell us about CMB-S4.
Okay, good. Thank you to the organizers for having me here and letting me talk about our pie in the sky concept, which we're trying to turn to reality now. So you've heard in the past couple talks a little bit about the ground-based program. You heard about bicep Keck. You heard a little bit about SPT2, in particular for delensing. You heard about the Simons program, Polar Bear Act. And this is the continuation in that story. What I have up here are pictures of the two prominent US CMB sites. So that's the South Pole. This is the old Bicep 2 telescope, which has now been replaced by Bicep 3. That's SPT. And Lyman showed you this, the video of the ACT and Simons Observatory site. And that's the ACT ground shield right over there. In closer view, these are the two sites, and these are their what we call stage 2 and stage 3 programs. Stage 2 refers to focal planes in these cameras that have about 1,000 sensors, 1,000 photon noise limited sensors, and stage 3 refers to something like 10,000 or tens of thousands. So this is what's there right now. Again, same thing. This was all talked about. There's class, there's Simons array, there's ACT. There's, if you will, a stage 3.5 program called Simons Observatory that Lyman shared with us earlier. And then this over here is a BICEP program and SPT. So CMB stage 4 is the logical extension of this program, and that's what I'm going to be talking about over the next few minutes. Very quickly, a word about ground-based CMB and space-based CMB and how they fit together. We heard in the morning quite a bit about space-based CMB and our ambition over there to really extract all the possible information we can get from polarization, from CMB lensing, and so forth. And so space-based missions are quite amazing. They offer this all-sky, all-frequency view of low to sort of mid, or even approaching high-resolution CMB science, illuminating this primordial gravitational wave recombination reionization peaks, lensing some of the secondary science, so heading that way. And they come at a cost, obviously. And unfortunately for us, they're infrequent. It takes a while to get these up and running. And so we see these every 10, 15, 20-ish years, as opposed to every 5 years if we could. That would be fantastic, but we don't. Ground-based CMB, on the other hand, fills in that gap, offers rapid progress in this mid to high-resolution CMB science area, which is the recombination peak of primordial gravitational waves, lensing, clusters, SZ. And this does come at a cost, which is looking through the 10 Kelvin of atmosphere, looking through limited atmospheric frequency windows, limited sky coverage, depending on your scan strategy, limited modes. So that is the price you pay. It does offer, of course, this feedback loop of technology for space missions. So whatever happens there sort of goes through this program and goes, in fact, to usually balloon-based CMB programs where they get space qualified, this technology, and then enable these ambitious space missions. So the ground-based program, in my mind, offers this avenue of rapid progress in the times between satellites and prepares technology for space missions. This I probably don't need to go over this again. I stole this from Jacques, or rather, he very kindly let me use this plot, which is observing frequency versus angular scale in the sky, and what the satellite missions sort of do or cover in terms of science, and the windows in which from the ground-based program ends up contributing. And this overlap in these areas is sort of our consistency check. Different systematics, different ways of doing the experiment and making sure we come up with the same result. Okay, expounding a bit on this, on the higher angular resolution sort of ability that we gain from the ground. This is a patch of 50 square degrees as seen by Planck, and it's the same patch as seen by SPT in higher resolution. So it's 13 times finer angular resolution, 50 times deeper, and you'll notice that some spots have come up, which are not just blemishes over here. They are actually things. So these white spots over here are point sources, active galactic nuclei, and the most distant, dusty star-forming galaxies, which then we can follow up with other ground-based program. Then these other spots over here, these black spots where the CMB light seems to be missing, is from the SZ effect, and this is how we've identified many, many clusters of galaxies. And that's something else that we can do from the ground with high angular resolution. Okay, so with that introduction and sort of telling you the role of the ground-based program, let me jump to CMB-S4. So S4 is our next generation ground-based experiment in the 2020s to pursue inflation, relic particles, neutrino properties, dark energy, galaxy and structural evolution, and hopefully make some new discoveries. There's a greater than 10-fold increase in sensitivity over the combined stage 3 experiments. This is accomplished by having hundreds of thousands of photon-limited sensors. Jacques told us that you need 100 times more than what you would do in space, and that's reflected over here. And so to try to do this from the ground, we want to deploy many hundreds of thousands of photon noise limit sensors, spanning all the windows, atmospheric windows that we can look through, using multiple telescopes, large and small, and this is for systematics reasons, at least in South Pole and Chile, 2 sites, to map most of the sky as well as get to some deep targeted fields. There's broad participation of the US CMB community in this, the existing CMB experiments, the US high energy physics community is entering, and their national laboratories. And I've underlined and bolded and italicized this. International partnerships are expected and desired. Okay, so this is an invitation. We're looking for partners. This is who we are right now. It's a growing collaboration with 190 members from all of these countries. We meet every 6 months. We recently met at Princeton, and our next meeting is in Chicago. And if you're interested in coming and checking out one of these meetings, you can go to our website and register there. There's a couple of products that have been put out explaining what CMB-S4 is. So there's a science book and a technology book with this sort of author/endorser list. You can find these online as well. There's another publication in preparation right now to go as an entry into the decadal survey to make our case to the astronomy community that this is something that's worth doing in the 2020s. So watch out for that. Okay, today's state of measurements and constraints. We've had many talks today on this. This is TTEEBB power. After the latest 2018 Planck legacy release. Lambda CDM is exquisitely confirmed. We've seen this 6-parameter model fit the data really well. However, extensions to Lambda CDM need to be probed much further, I contend. We know we have a flat universe. The N sub S is not 1, but we haven't seen primordial gravitational waves yet. Maybe inflation is still lurking out there. And R is constrained to be less than 0.07. And then there's much untapped information, all of here, from the effect of CMB backlighting, beyond just the E mode, so the lensing B, clusters, KSE, and so forth. And so the story that CMB polarization tells us is just starting now, and we want to exploit this. So CMB-S4, sorry for the color over here, aims to probe cosmology, fundamental physics, and astrophysics are our two main drivers at the moment as we are preparing our science case, are inflation and light relics. Inflation, we would like to measure the primordial power spectrum better, tighten constraints on n sub s, non-Gaussianity, and of course measure tensor to scalar ratio or set stringent limits on it. Light relics as measured by an effective, sum of neutrino masses. And if we put together an instrument that does these things, we get a bunch of ancillary science, including probing growth in a variety of different techniques. We hope to be able to test GR on large scales. I mentioned earlier the dusty star-forming galaxies. We hope to continue to image many, many more of those. Constrain the duration of reionization, evolution of structure, looking at the dynamics and kinematics of electrons and thermal dynamics in galaxies and clusters. This is our projection for what our error bars could look like with CMB-S4, and this plot, this usual power spectrum plot, has data from these experiments. All the stuff from Planck is in black. Probably hard to see the colors over here. You can go to the CMB-S4 science book and get a better version of this plot if you'd like to study it in detail. What I want to point out over here is this band over here, and if you follow it, it thins down to the line. That's how well we hope to measure E modes, and over here you can start seeing individual error bars. Similarly for lensing B modes. Okay, so this is what we hope to enable with this next generation program. This is enabled by this relentless march in sensitivity, and I'm talking only about raw experimental sensitivity. I'm not talking about, obviously there's the incredible effort for foregrounds removal, delensing, and so forth to convert this into science results. But starting with WMAP, WMAP and Planck are shown over here as a space-based experiments, but then here you see the stage 1, stage 2, stage 3, and stage 4 raw sensitivity that has happened rather rapidly. So this has been a span of a little bit more than 10 years where this stamping out detectors has sort of become efficient. We talked a little bit about yield. We said that we accomplished something like 70% yield, but these numbers are impressive because there are orders of magnitude increases. And I forget whether Rita showed this particular chart or not. This is just the example of the BICEP program, and similar plots exist for SPT, for ACT, for Polar Bear. But basically, with modest beginnings, about 10 years ago, the program has scaled up because of this photolithography-based production of bolometers for CMB. And so we went from 500 sensors to 2,500 sensors across 5 cameras, and 2,500 sensors in 1 camera, making that even bigger, making more and more of these detectors, to the point that the BICEP array, as Rita was talking about, is about 30,000 detectors. And this is exactly what we wish to continue over the next several years to get to CMB-S4 with 500,000 photon noise limited sensors. Okay, so this is the reference configuration. So this is what we're trying to put on paper right now. It's got 8 optical bands from 20 to 270 gigahertz in all the atmospheric windows. Some of those windows are split into subbands. I'll show you in a second. There are 0.5 meter and 6 meter aperture telescopes in Chile and South Pole. And of course, you're hearing now this is very similar to the Simons program, to the BICEP array program. So this is somewhat of an extension that way. We want to target 3 to 8% of the sky for a deep survey and 40% for a wide survey, getting to 1 to 2 arc minute, micro K arc minute sensitivity. These are the toy models of the cameras. This is the NEMAC design that has been talked about already. So the reference design for CMB-S4 includes stamping out a few more of these fed by cameras that have more optics tubes than the ones you've seen so far. And so 3 of those, okay, so 3 of these things, and 18 small telescopes. So 18 BICEP 3 type of cameras for the low resolution primordial gravitational wave science. There's a split of detectors. I'm not going to go into this mostly because this is an earlier configuration. I'm just showing here as an example. This is not the current configuration. The number over here adds up to 372,000, and as we've refined our projections, we've realized we need more detectors to hit our science target, and so that number has gone up to 400 something, and you'll see most of it comes from this 14 to 18 cameras. But anyway, so we have a lot of these bands. You see that there are projections that have been done that tell you the number of sensors per band as well as the angular resolution that we think we can get. But anyway, there's an updated version that you'll see hopefully soon in a paper that's put out. Telescopes in Chile and South Pole to cover a large fraction of sky. So that's the Chile observable sky, that's the South Pole observable sky. That covers 70%. We think 40% is usable. And as Lyman was pointing out, this enables us to overlap with a lot of the larger optical surveys and do cross-correlation analyses with these upcoming optical surveys for dark energy. We're probably not going to end up using a lot of yeah, that's right, yeah. And I should note over here, a northern site would complete sky coverage, as somebody was, Tarun was talking about earlier. So that's, if you know of a site in the northern hemisphere that might help in the program, we should talk about it. Okay, let me quickly get to some science projections. So this is our inflation constraints projection in the tensor to scalar ratio versus spectral tilt plot. This blue region is the current allowed region from, this is slightly older, I guess, this is BK14 and Planck. There are stage 3 projections over here, and this is stage 4. The red area is where we want to get to. Constraining R to 10 to the -3 at 95% confidence, or to make a detection of R equals 0.003 and rule out large field inflation. There's some models over here. There's the Higgs model and Stravinsky model. I said that backwards, I think. Stravinsky model, Higgs model. So to do this requires an extensive multi-frequency, small and large angular scale deep field measurements. If you actually see something, then you want to do many such fields or a wide field measurement of the type that Lyman was talking about. So we want this drives us to an extensive program from the two sites to make this measurement. Next, let me comment quickly on light relics. So N effective is what we're after. The effective number of neutrino species, let's put that in quotes, measures the total energy density and radiation apart from photons. In the standard model, that's that number. And this, I think, if I grabbed it from the right place in the paper, this is the current measurement. And what we hope to do is this. This is a plot very similar to what Shaul showed earlier for Pico. So this is delta N effective, or the departure from that 3.046 versus the freeze out temperature of a thermal relic, and we hope to constrain delta N effective to less than that line over there. So rule out all of this. And if you take this and you pick a particular model, so for vectors, that means that you've gained nearly 2 orders of magnitude beyond the QCD phase transition. So going past the QCD phase transition and ruling out relics up to that freeze out temperature. And this requires a small angular or high resolution wide field survey, and so this drives all of that set of instrumentation. Put those two things together, and the instrumentation you end up with enables a lot more science, obviously. And just to give you a flavor, we hope we'll have transformative advances in, of course, CMB lensing to map the mass distribution of the universe, 3D tomography with optical shear and redshift surveys, and measure neutrino mass sum. This is more limited by tau. So unless somebody goes and measures tau, we're not doing that much better. So that's not a driver for us. SZ, of course, constrained reionization, a definitive survey of high Z galaxy clusters with the CMB lensing mass calibration, so hopefully see about 100,000 clusters. And then what I was saying earlier, mass profile, gas temperature, and density profiles to determine the role of baryon feedback. So there's tremendous discovery potential, and one more thing, which is we hope that this instrument will be maybe the first, perhaps not the first, but at least a millimeter wave synoptic survey, where we're able to do daily monitoring of thousands of square degrees at multiple wavelengths and polarization, and can perhaps see transients, right? So always on, checking for sources, because we have this millijansky sensitivity per day to see this variation. And there's also thermal detection of solar system objects, Planet 9, and so forth, that actually can show up in our maps, and our simulations show that we have some pretty good sensitivity over here. So I'll wrap up there. Hopefully that was a good overview of the high-level CMB-S4 plan. So this is a 4th generation ground-based CMB program. It is being mobilized to do the near ultimate CMB polarization science that is accessible from the ground, right? We absolutely need to go to space to do the ultimate polarization survey. But in the meanwhile, we hope we can do this. We will probe inflation relic particles. I mean, this is stuff that I told you earlier. And very importantly, looking for partners. So with that, I thank you for your attention.
Time for questions.
So there seems to be, a problem with the high frequency part of the foregrounds. So how do you plan to control that? Last contribution.
Right, so we're able to go up in frequency only to something like 270 gigahertz. Our dust monitor channels will be, you can go back and look at that. So we have 220 and 270 at the moment. We do include all the Planck data, the WMAP data, but we are limited in that way. That is correct. Our simulations, of course, assume that, and our component separation models assume only the channels we have available. And so that's how we're setting our science targets.
Yeah.
So you mentioned in one of your slides that Higgs inflation leads to R of order 0.003. And you said that if R is less than 0.003, then all the large field models are ruled out. Do you know which model you are referring to here? Because
so I mean, I shouldn't say all. This is a large class, is what is meant to say over here. I should be a little bit more careful in how I'm saying this. This is basically saying all sort of another way this has been said is models that sort of naturally explain n sub s, are ruled out. I mean, basically, the class of models that is above that are 001. Yeah.
Rashid?
Are there any plans to use to build something in the S4 program for Greenland or something?
That's an excellent question. In the baseline program right now, it assumes only South Pole and Chile. But as I've been saying, in extensions to the program, which might be possible if we have larger international participation as an example, we could consider developing sites and instrumentation in the Northern Hemisphere. It's not part of the baseline plan, but we would love to see something like that. Greenland as a site has been evaluated. It is generally understood that the infrastructural challenges are a bit higher in Greenland. than the established sites and a couple of other candidate sites in the Northern Hemisphere. So Lyman mentioned the Tibetan site. There's an Indian site in the Himalayas as well, which is actually just like 50 kilometers away from the Chinese site, from the Tibetan site. Those two sites have better infrastructure. Those could be candidates for a Northern Hemisphere survey.
Okay, let's move on.